Let's see, I'm missing some files from last time. I know I put them out there, but I can't see them. So I must have put them somewhere else. And then I guess another course is going to be very confused, but I'll find them. I'll find them and put them out. Today, advection. Last time it was wave, so now advection equation. And I'll start with a very classical example. It's a steady state problem, so not a transient one. Example, steady to the advection equation. You have a two-dimensional region in space, xy, xy, like this. Simplicity, we say it is square. We have the same number of cells in both directions when we now do discretization here. And then we will look upon transport of an unknown function phi. So here I now have a constant velocity u in the x direction. Here constant velocity v in the y direction. So the velocity vector is going like this. And also here I will send in a concentration or a function, say phi equals 1. Down here I send in phi equals 0. And then it's a question, how will the phi look inside my domain? The two-dimensional advection equation describing this now being u the phi dx plus v the phi dy equal to 0. Equal to 0 meaning you don't have any viscosity on the other side, no diffusion mechanisms. So then physically what should happen is something like this. The diagonal here should be a sharp jump between 0 and 1. So that must be the correct physical solution for this problem. Just pure transport of this function phi, whatever that might be. And now we do it easy. We say u equals v equals 1, dx equals dy, say equals h or whatever. And then you make a discretized version of this one. Okay. If you look at a central space scheme, typically what you start with, you try that one first. Discretize that one using central space schemes. Okay. Discretizing the normal way, I, j for x and y directions. Then first term here should read something like u phi I plus 1 j minus phi I minus 1 j divided by 2 delta x. And then you have the same term in the y direction, but now I j plus 1 minus phi I j minus 1 divided by 2 delta y and then equal to 0. Solve that equation system. Here you now have a discrete equation, but you see the center point doesn't enter the equation system at all. So how can this be solved? Well, that can be a big problem. You can't use a direct method here. If you set up the matrix, you see the diagonal is 0. It's not present. So it's not going to be solvable. Never mind that, we're going to solve it anyway. But you will have problems with the advection equation and central schemes. As I guess you have seen already, with time, unconditionally unstable, it explodes no matter what. So what's the remedy? we use first order upwind scheme. First order upwind is a terrible scheme, stable, but we don't like it, and here you'll see why. Now, first order upwind, then you have to take into account the sign, the transport direction, and when you then create the derivatives, you say the information is traveling in this direction, so I create the derivative upstream, upwind, depending on the velocity. So here you will have u, and now phi ij, the center point, minus I minus 1j, divided by one single delta x. Same goes in the y direction, phi ij minus ij minus 1, and one single delta y. So there you have the derivatives, first order upwind. So let's try both of these and see what happens. Okay, let us try to make a little program. Clear all, close all, and CLC. So there we go. We need a number of unknowns, so if I now start with, say, 20, I can write my unknown phis. I use large F for phi. Set everything to zeros of n. There I have a n by n matrix. F initialized to be 0. Then I need the right hand side, sorry, the left hand wall as a boundary condition. So the first ones, everybody equal to 1. So that should be our function f now. Yeah, we can just leave it like that, should be okay. Then we start with our first order scheme. Start with that one. Now I skip the boundaries, of course. So here I go all the way from 2 to n minus 1. Actually, I don't have to stop at n minus 1 for this one. You see, you can calculate the center point ij depending on the left neighbor and the one below you. So you can take it all the way up to n. You don't need a boundary. Here the information is traveling up and to the right, meaning the top and the right walls, they don't need boundary conditions when you are thinking in terms of upwind. It's not necessary. The same goes then for j. Start by 2 and then all the way, including the boundary. That should be possible here. What will the recipe look like? Well, if we simplify here a little bit, remember it's 0 on the other side, u is 1, v is 1, delta x and delta y are equal, can be removed since it's 0 on the other side. And then you see you have twice the center point equals the sum of these two guys. So the recipe should then read something like Fij equals the sum of these two other guys. That was Fi minus 1j, and it was Fij minus 1, and then divided by 2. That should be the recipe, if I have calculated it correctly. And that's it. So there we have a solution which we then can easily plot. I want to have sort of contour lines, and I want them to spread out from 0 all the way to 1 with step 0.1. So I use this v vector to specify the level of my contour lines. Then I can write contour like that, and I want f, and I want it according to this v. Now sadly, the way MATLAB operates, he flips x and y direction, at least in my opinion. So here I have to transpose this f if I want to have it the same way as I have my drawing. So let's have a look at that one. There you go. So there you see what happens. You send in a value of 1, and here a value of 0, and everything is just spread out. So here, of course, in the corner you will have a singularity. Depending on how you program it, one is 1 and the other one is 0. So of course over one single cell here you will have a singularity. It's very hard gradient down here. If you want it a little bit more colorful, you just write contour, what is it? Contour F, is it? Then it's filled. So we have a smearing effect, and this should not be present. We should have a sharp jump here, and you don't get it. You can of course increase the number of cells. I had only 20 by 20, so 100 by 100 helps a little bit, but not perfect. Even got some noise up in the corner there. No. So first order upwind scheme, very diffusive. We don't like it, but sometimes we have no choice, we have to use it. Questions so far? That's okay? Yeah.
Question, the V vector, what exactly does it do?
It's a cosmetic thing. When you write contour, by default he will give you 20 lines from max to mean. I don't want that. I want them exactly given as these levels. So if you specify a vector here, you are going to get these lines with these values. So that can be convenient, say if you want to plot the stream function or something and you know he changed it from 0 to 1, or you are interested in some particular value of the contour level and so on. Then you can specify it here. Instead of specifying 500 lines, for instance, if you're interested in some nasty area, nasty value area that the ordinary contour doesn't take by default. Other questions? No? Let's try the other one. I call him for phi number 2. So I make a copy up here. Then I have included the boundary condition. But how to program this one? We can simplify it by saying, okay, you have equal to 0 here also on the other side. Delta x equals delta y can then be removed. U equals v equals 1. So still you have an equation system that sort of seems impossible. But here with this problem, given that we know the solution, or at least the values to the left and to the bottom, we can solve it more or less in the same way as the upwind scheme. We can sort of march the solution forward, either upwards or to the right. That should be quite possible here. I chose upwards. So normally what you would do with a given equation, you will focus on the center point. You will pick up the center point and write it on the form center point equals, and then everything else on the other side. Here you don't have the center point, so you have to choose another one. So here I chose this one. Then write the recipe on the form j plus 1 equals, and then just throw everything else on the other side. So what will it be? You will have minus I plus 1j plus I minus 1j plus, and then this one phi I j minus 1. So I programmed that one instead. Let's see if that one works. So we have the same loop for I equals 2. And could we take that one all the way up to n for I? Well, actually no, because then he will explode. So I have to skip 1. That shouldn't matter much. But for j, 2, that one can go all the way up. That's okay. I don't have j plus 1 on the other side, so he should be okay. And then we follow the recipe, f, and then it was I j plus 1 equals. But then you see the problem. If I choose this one, just following the notation, I can't have n here. Then I will go outside. When j equals n, I will have n plus 1. So I couldn't do it anyway. Okay, and on the other side we had f I plus 1 j. We had that one was negative, minus, and then it was plus I minus 1 phi I minus 1 and finally I j minus 1. So let's create another figure and plot him as well. With the same isobars. So there you see also a nice way when you want to compare and you want then exactly the same values for the isobars. So let's see if this one works. Not well. What did I do wrong here? Phi I j. Thank you. Of course it should be f number 2, not f number 1. Let's see if that helps. That helped. Thank you. So there you see it. You get it perfectly. So it's possible, yes, actually, to use central scheme on this problem. You're solving the advection equation, and the solution is just perfect. But here we needed some trick to make it work. We had to program it or solve it quite specially, actually. Any questions to that one? It's okay. Let's just take a look what we are actually doing here. Shouldn't take too long. If we look at this one first. Let's see, we need this one. I mean, you have seen this already in class. you have a scheme. Is the scheme consistent? What's the order of this scheme? Find the modified equation for it. That's a way to see what this scheme is actually doing, how well it performs. So checking for consistency, well, you should always get your original partial differential equation back, or else there's something wrong. And for the first order upwind scheme also, is it consistent, and so on. So how to check for consistency? You take the Taylor series and then you insert anything that is not sort of the center point value. So here you need a plus Taylor series, here you need the negative Taylor series, and here both of them, but then in the y direction. So you have to insert, say, plus minus 1 in the x direction. You insert the center value I, and then depending on the direction you will have delta x or y, whatever, phi derivative, and then delta square, half, phi double, and so on along the line. If you insert this series here, what happens? Well, we have u divided by 2 delta x on the outside, and here the difference between these two series, you see the center point will fall. Here you'll have plus this term here, and then minus minus the same term, so you have him twice. So you'll have 2 times delta x times phi derivative. So that's him. This one will disappear. Both of them are positive, but I have the difference between these two series, so he doesn't survive. The next term, third order, he will survive. So I will have something with delta x to the power 3, phi 1, 2, 3. Something like that. And then even higher order terms. And same goes now in the y direction. I don't even bother to writing it up. And there you see what happens when you multiply in here. You see you get u phi derivative here with respect to x, of course, which is exactly what you should get. And then you will have plus a term here, which then should read something multiplied with delta x square. So from this you can conclude the central scheme is consistent. When the delta goes to 0, you get your original partial differential equation back. The order, second order accurate, so no problem at all. Questions for this one? I don't go into all the details, writing it completely out. You can see that one for yourself. Now do the same with this guy. Then what happens? Well, you need here u over delta x outside, not the factor 2 anymore. Then you have the difference, center point minus the negative series. So the center point will fall. Then you will have minus and minus, which then will become plus. So here you'll have delta x phi derivative. That looks okay. That was the second term. Third term, the double derivative, he will be negative then. Minus, and we have delta x square half phi double, and then higher order terms. And then similar in the y direction. So what do we get now when we insert here? You see you can write it on the form u phi x derivative. That's okay. That's our original equation, which we like. No problem there. This term I throw on the other side. just on purpose. Because what does he look like? He will be something like u 1 delta x half phi double, and then even higher order terms. Now, only have looked at the x direction, of course. Again, the scheme you can see is consistent. Let the deltas goes to 0, you're back to the original equation, so that's okay. Here, it's only first order accurate. This is the first order term, order delta x. But now you see, as compared to the central scheme, there we had something with the third order derivative. Here I get an adder with second order derivative, positive. There you see the diffusion. So this will act as a diffusion mechanism, sort of with a viscosity here, or diffusion coefficient, that makes the equations be smeared out. So the modified equation there is very convenient when you want to see what the heck is actually going on. So there, the central scheme, more accurate, no diffusion. First order upwind, less accurate, with a lot of diffusion. To get the adder small, it's only one remedy here. Smaller and smaller delta x. Yes, we can use very small delta x, but of course it's going to be limited here. Say, he can't do that. Let's try it. 1000 by 1000. He could. This was the central scheme, just perfect. The upwind scheme, you still see the smearing effect. It's not good. It's going to be smaller and smaller. I think this one is the 0 line, so don't worry about him. Smaller and smaller, but still you'll have this diffusion effect. Smearing out. No questions to that one? Okay. So last time we looked at the two-dimensional wave equation, and at least now this file should be out for you. And just to recall what this was all about, I looked at a rectangular area in space and then looked at a surface wave. Here an initial disturbance with like a cosine. The corner lines there to the right, they are just scales. So letting the wave go, you will see he reflects from the borders, and then you get, of course, here in the end a lot of noise. So that's the two-dimensional wave equation. Double derivative in time and double derivative in space. The boundary values here, that's a Dirichlet condition, see 0. You could make it with a Neumann condition. You will get the same image roughly in the end, a lot of waves going back and forth. So that's what we did the last time. As a question for this problem here, another way to solve this system, instead of looking at a steady state problem, why don't we just add time? So that can be done, and frequently it's done on purpose. When you have a problem and it's a steady state problem, you're not interested in any time development, but to achieve a solution you can add the time derivative in front of it. So what we are looking at now is a transient two-dimensional advection equation. So now we are talking time derivative. I go back to my signal u as the unknown. Could have used phi as well, but never mind that. Then here I need a constant velocity. I'll just call him a0. X derivative and the same velocity, and now y derivative equal to 0. So there you have a transient version then of the advection equation. Just added the time derivative in front. That's it. Now solve that one. So first we will have the obvious choice, as always. Forward time, central space. Should now be straightforward. Forward time, then you need for the center point time level n plus 1 minus time level n over 1 delta t. And then plus and so on and so forth. For these terms now, center point, you will write a0 u I plus 1 u I minus 1 over 2 delta x. And same goes in the y direction. J plus 1 minus j minus 1. 2 times delta y equal to 0. That will be the central space scheme. What about the upwind? Well, then we have to know something about the transport velocity. Somebody has to tell us. Is it positive, negative, what is it? So here I assume it's positive. Then my upwind scheme will look something like this. A0 uij minus ui minus 1j over one single delta x. That's the only difference. Same goes in the y direction. Ij minus uij minus 1. There you have the two stencils. So I now use this program here and just modify it to cover our needs. So we have to call it something. Wave, what should we call it? Yeah, I'll call it advect number 2. Ah, I have to remove that one. Now using the same area, rectangle 10 by 7, and then delta x equals delta y. My area goes from minus to plus, so it's actually 20 by 14 in range. Never mind that. Here we have something called a Courant number. Well, we still have that. If you take your schemes and rewrite them on the form center point equal to, then you write them on an explicit form, of course. New one equals, and then everything else on the other side. You'll see you'll have a over delta x multiplied with delta t. So yes, the Courant numbers, they are going to pop up here clearly. So we can keep him. We just leave everything else as it is. The scales here should be okay. Initial disturbance, that one I'm going to change. I don't want a sine wave as a disturbance. I'm going to just use a flat one. Just say that he is equal to a in a certain range here. Then that should be all we need. New u we need, the old one we don't need. So let us now try to make the here it was the wave equation we have programmed. Remove that one. For the temp, what will the FTCS look like? Well, fairly easy. You have the center point here, And here you have all the 4 neighbors, so they have to be on the other side then. Let's see, it should be I plus 1, I minus 1, but that one should be negative, shouldn't it? Yes, he must be minus. J plus 1 should be plus, J minus 1 should be negative. So there we have the 4 neighbors, and then we should be able to write it something like this. We have that one, we have the Courant number multiplied with our temp. Let's see, is that one correct now? We better write it out explicitly so we can see it. Isolate this one. Uij n plus 1 equal Uij n on the other side, and then you will have minus. You can write the Courant number outside, delta T A0 over 1 single delta x, and then you will have all these, that one, that one, that one, divided by 2. That should be the correct one. So I think I need a minus there, and I need divided by 2. Now it should be correct. Then we can update and plot. Everybody agree it's correct? We try. So this is the initial state. Everything is 0 except a square region where I put the value 1. Now the transport equation says move in the positive direction. So he should move to the right and upwards. He's not moving at all. He's just moving very big numbers. So something is fishy. He's even moving the wrong way. If he's moving, not easy to tell. Clearly unstable. So what do we have to do? Smaller time step. Doesn't look promising. He spreads out and gets higher and higher and higher, explodes. So here it really doesn't matter what you do. You can use a small time step as you like. It doesn't help. Unconditionally unstable, no matter what you do. So here you have no chance of getting a solution. Strangely enough, I mean, the steady state problem, we could. That was a little trick. We had to program it a little specially. But here you see it doesn't help with small delta t. He still explodes. Can you see that from the equation system? Let's try it. Then I have to remove the upwind. Should be okay. If you write it a little bit nicer, Uij n minus the Courant number C multiplied with what will we have here? We have Ui plus 1j, Ui minus 1, and we have plus Ui j plus 1 minus Ui j minus 1. And then divided by 2. So here you could use a stability analysis on this one, and you will find unconditionally unstable no matter what. According to this numerical stability method, the very quick and dirty one, if you add all the coefficients together, you'll see here all the coefficients, they will cancel out. Plus 1 minus 1, plus 1 minus 1. So regardless of c, they will disappear, and you're left with a coefficient of 1. But then the demand was all coefficients should be positive, and you see that's not possible here. So yes, it's true, it's unconditionally unstable. You can't hope for a solution. Any questions? Then we try with an upwind scheme after the break.